All right, in section 6.2, we're going to talk mainly about orthogonal sets, and then we'll get into orthogonal projections as well. Now, we saw the idea of being orthogonal, of two vectors being orthogonal in the last section. So just as a reminder, two vectors are orthogonal if their inner product it turns out to be 0. So what are orthogonal sets? Quite simply, they're going to be sets of vectors which have the property that each vector is orthogonal to each other vector in the set. So an orthogonal set is in some sense a collection of vectors which are all orthogonal to each other. So I want you to check to see if this set is an orthogonal set. Go ahead and push pause on the video and check to see if every vector is orthogonal to every other vector in the set. All right, hopefully you went ahead and did that. So if we take this set, we're going to take 4, 1, 2 and inner product it with -1, 2, 1. Let's check that one first. So you're going to get -4 plus 2 plus 2. Yes, that's 0. So the inner product of the first two vectors are 0. Remember, order doesn't matter. So if you took the second inner product with the first, you'd also get 0. So there you go. Let's take vector number 1 and vector number 3 there. 4 times 3 is 12, plus 1 times 6 is 6, plus 2 times -9 is -18. Sure enough, you get 0 when you multiply vectors 1 and 3. And then vectors 2 and 3, you get -3 plus 12 minus 9, which in fact is 0 again. So notice that no matter which two vectors you choose from this set of 3 vectors, any pair is orthogonal to, and therefore this is an orthogonal set. So this set here is orthogonal. Now I want you to do the same thing with this set of vectors. Ask yourself, is the following set of vectors an orthogonal set? Go ahead and push pause on the video and check to see whether this set is an orthogonal set or not. All right, so hopefully you went ahead and did that. So we're going to take this vector 1 is 203, vector 2 is -352, and vector 3 is 6, 4, -4. So if I take vectors 1 and 2 and take the inner product, we get -6 plus 5 plus 0 plus 6, and that gives me 0. So vectors 1 and 2 are orthogonal. How about vectors 1 and 3? So if I take vectors 1 and 3, I get 12 plus 0 minus 12, which is 0. That's a good sign. And vectors 2 and 3, I'm going to get -18 plus 20 minus 8. Oh, that doesn't work out. That gives me a -6. So while vectors 1 and 2 are orthogonal and vectors 1 and 3 are orthogonal, vectors 2 and 3 are not orthogonal. And therefore, this set is not an orthogonal set. Okay? So there it is. Now we can quickly transition from the idea of an orthogonal set to the idea of an orthogonal basis. So imagine we have a subspace W. An orthogonal basis for a subspace is a basis which is an orthogonal set. So a basis which is an orthogonal set is called an orthogonal basis. That should be pretty straightforward linguistically. Now, it turns out that the example I had at first, this orthogonal set 4, 1, 2, negative 1, 2, 1, and 3, 6, negative 9 is in fact an orthogonal basis for R3. I won't go through the details, but basically we have three non-zero vectors and they're all orthogonal, so you are going to get a basis for R3 in this situation. Now the interesting part about an orthogonal basis is what happens when I write a vector as a linear combinations of vectors from the basis. Okay? Specifically, if I have an orthogonal basis for some subspace W, then I can write any vector in W as a linear combination of those basis elements. So let's say U1, U2, U3, U4 is an orthogonal basis, and I write my vector Y as a linear combination. It turns out the coefficients for each component, the coefficients of each basis element, have a really nice formula. It's the inner product of Y and UJ, whatever one we're talking about, divided by UJ inner product with UJ. Now remember, inner product gives you a real number, so we take a real number here, real number there. Now this is in fact pretty easy to see. Let me do an example here. So let's pull up this example. So here we go. So how does that turn out? Let's say I wanted to find C2. Well, what I'm going to do is I'm going to take this equation here that, let me just copy that and repaste it. And I'm going to, on the left-hand side, do an inner product with U2. And on the right-hand side, do an inner product with U2. Okay? Now, on the left-hand side, obviously that's just Y inner product U2. So that's nice. On the right-hand side, if you remember about inner product, the inner product distributes over addition. So all we're going to end up with is the following equation. So inner product Y inner product U2 is equal to C1 inner product, U1 inner product with U2, C2 inner product with U2. So each component we're going to multiply by the inner product of U2. And now because it's orthogonal, U1 inner product U2 turns into the real number 0. U2 dot U2, that's just some real number. U3 dot U2, again, they are orthogonal. So we end up with 0. u4.u2, we're coming from an orthogonal set, so inner product is 0. So when you take the inner product, everything goes away except for that C2 times U2 inner product with U2. And then so the coefficient, all I have to do is divide by U2.U2. So it's equal to Y, oops, dot U2 divided by U2 dot U2. So basically, because of orthogonality, those coefficients are really, really easy to come up with. Okay? So I have a way, a quick calculation way to come up with coefficients when I write my vector as a linear combination of basis elements from an orthogonal basis. So let's go ahead and do that. Let's try to, with this set, which we already have established as an orthogonal basis, let's try to find the coefficients when you write 7, 8, 11 as a linear combination of these three vectors. Go ahead and push pause on the video and see if you can do that. All right, so here's what I went ahead and did. Now, here's how we're thinking. We're thinking that 7, 8, 11, make sure I got that vector right. 7, 8, 11 is a linear combination of these three elements. Now, we just saw that if I want to find the coefficient, I can take the inner product of my vector 7, 8, 11 with any one of these vectors and then divide by the inner product of the vectors. So basically, when I go to find, let's say, C1, all I have to do is I have to take my 7, 8, 11, inner product. You know what? I don't know if this will work. There we go. Inner product with 4, 1, 2. And then divide it by the inner product of 4, 1, 2 with itself. Okay? Now, this is just going to be some real number. Let's go figure out what this is. 7 times 4 is 28. Obviously, it's going to be some fraction. So we're going to get 28 plus 8 plus 22 on top. On bottom, I'm going to get 16 plus 1 plus 4. So what we get, 28, whoops, 58 over 21. There you go, 58 over 21. Now, 58 over 21, don't know, that does not simplify. So that's it. 58 over 21 is coefficient 1. Now, we do the exact same process for coefficient 2, except obviously when you do coefficient 2, instead of using 4, 1, 2 as my vector of interest, I'm going to use negative 1, 2, 1 as the vector in my basis. So replace all the 4, 1, 2s with negative 1, 2, 1. Let's go ahead and do this. So 7 times negative 1 is negative 7. 8 times 2 is 16. 11 times 1 is plus 11. With the with the denominator here, negative 1 times negative 1 is 1, plus 2 times 2 is 4, plus 1. So what we're getting, negative 7 plus 16 plus 11, means that that is a 20 in the numerator. And in the denominator, we're getting out a 6. Okay, so 20 over 6. That one does simplify a little bit. If you wanted to simplify it to 10/3, you could do so. Same thing with C3. Whoops. For C3, let's control copy, control paste here. So with C3, it's the coefficient of my third vector in my basis, which is 3, 6, negative 9. So I'm going to take inner product of 7, 8, 11 with 3, 6, negative 9, and then divided by 3, 6, negative 9, inner product with itself. By the way, notice that the denominator is just the square of the length. So we get numerator over denominator. Numerator is going to be 21 plus 48 minus 99. By the way, let me just go ahead and calculate that. That is going to be a negative 30. Let me put the negative up there so that looks a little bit nicer. Denominator is going to be 9 plus 36 plus 81, which is 126. Okay, that does simplify a little bit. I think they are both divisible by 6. So if you wanted to, you can call that negative 5 over 126. Hopefully that's divisible by 6. Yep, 21. So negative 5 over 21. So there you go. That is how I'm going to erase this just so it fits on one line. Oops. Oh, there we go. So negative 5 over 21 is the coefficient for C3. Now you can imagine that finding these coefficients by hand, notice how ugly these fractions are coming out. Finding these coefficients by hand would be fairly cumbersome. We could, obviously row reduce with our calculator, but this gives me a really efficient way to find these coefficients as well. All right. And in particular, this way allows me to find a single coefficient like C2 without even knowing the others. So I found coefficient C1 without having to find a coefficient for C2 or C3. And that turns out to be an important property in the next sections. An important property when we want to build bases and things like that. So what I'd like you to do on your own is push pause on this video and try to find the coefficients using the same basis when writing 10, negative 5, 0 as a linear combination of the basis vectors. Okay, so we want to write 10, negative 5, 0 as a linear combination. So what's the coefficient I need on 4, 1, 2? I'm going to take the inner product of 10, negative 5, 0 with 4, 1, 2. Divide that by length of 412 squared, so inner product of 412 with itself. I've already set that up. We're going to end up with 40 minus 5 plus 0, which is 35, over, notice that the inner product in the denominator doesn't change from the last problem, 16 plus 1 plus 4, which is 21. All right, so this simplifies to 5/3. With coefficient 2, coefficient 2 is going to be using the -1 to 1. So I'm going to inner product that with the 10, -5, 0. You're going to get -10, -10, 0. That comes out to a -20. Hopefully I don't have to write that out, but -10 minus 10 plus 0 is -20. -1 times -1 is 1. 2 times 2 is 4. 1 times 1 is 1. So again, we're dividing by 6. That does simplify to -10 over 3 if we want to simplify it, or -10/3, however you'd like to say that. For the coefficient of C3, again, we're using 3, 6, -9. So we're going to inner product that with 10, -5, 0. 10 times 3 is 30, minus 30 plus 0. So notice I end up with a 0 on the top. And on the bottom, not that it matters, but I get 9 plus 36 plus 81. 9 plus 36 plus 81 was 126. Which, by the way, just means that the coefficient of C3 is 0. Just as a sort of side note there, if you'd put that in, what we get? 5/3 as the coefficient of 412, -10/3 as the coefficient, and then 0. What this is telling us is that my vector 10, -5, 0 is actually just a linear combination of these first two. Okay, so there we go. That's how we would write 10, -5, 0 as a linear combination of these three vectors. Now, the nice thing about those coefficients, like I said, is I can calculate one independently. And that's going to come in really handy when I do the next idea, which is called orthogonal projections. So the goal of orthogonal projections is to write an arbitrary vector as a sum of two pieces. Now we're going to have certain conditions on these two pieces. First off, we want these two pieces, the y hat and the z, to be orthogonal to each other. So we're going to break it up into two pieces. One of the pieces, or excuse me, these two pieces will be orthogonal to each other. And moreover, y hat is going to be in a certain direction. Now, what I mean by a certain direction is it's going to be along the same angle as some vector u. Okay, so I'm going to choose a vector u, and I'm going to say, well, what's the orthogonal projection onto that? That's the y hat, and then what's the piece that's orthogonal? I'm going to try to give you a visual of what's going on the best way I can. All right, so let's go back to that graphing of vectors thing we were doing earlier. Now, hopefully, you remember how we did this. We have just two vectors randomly graphed. So I have the vector 6, 3 and the vector 2, 4. Now, let's say I want to break up the vector 2, 4 into component pieces. One of the pieces is going to be along or in the same direction as 6, 3. So what would happen there is I would take 2, 4, and basically I would create, and I can't do this very well right now, but oof, this is bad. I would create, let me undo that. Two, 4 as a sum of two vectors. Okay? One of them is going to be along the line segment that goes from 0, 0 to the point 6, 3, so in the direction of vector 6, 3. And the other will be orthogonal, and it will make up, the other component. Now, if you think about what this is doing, this here is going to be my y hat, this black vector from 0, 0 to this point, and this vector is going to be my z. All right, so this y is going to be a sum of y hat plus z, and y hat is going to be in the direction of some vector u. So that's the idea. All right, so that's the idea of what's happening today. All right, so we're decomposing y into orthogonal pieces, one of which is in a direction that I want to go, a certain direction along a vector. Okay, now here's what we're going to do. In order to force this y hat to be in the direction of u, I'm going to force y hat to be some scalar times u, and obviously I want z to be orthogonal. So what's this scalar going to be? Well, for the same reason we had earlier, think about y hat being some scalar times u and z orthogonal. If I just dot product both sides by a u, the left-hand side is going to be y times u, and I say times as inner product. The right-hand side is going to be y hat, that's scalar times u, dot u, and then the z dot u will be orthogonal, so it'll turn out to be 0. Hopefully I don't need to go through that, but basically the coefficient is going to be y inner product with u divided by u inner product with itself. So again, we can think of these as almost like basis elements, although z technically could be a sum of many basis elements. All right? And this y hat that we're obtaining is going to be called the orthogonal projection of y onto u. All right, we saw the picture we had earlier. It's the orthogonal projection of y onto u. And it's denoted by this. When I write PROJ for projection, in parentheses of y, and this little subscript u is just going to be the coefficient we just found multiplied times vector u. Again, remember these inner products are giving us real numbers, so this is just some real number fraction multiplied times u. So this is going to be a vector itself. Now the other part is the z part. This is going to be the component of y, which is orthogonal to vector u. Okay, so z is the component of y that's orthogonal to vector u. So let's do an example here. Let's take a y and a u and find the orthogonal projection of y onto u. And then we're going to find the component of y that is orthogonal to u. So in other words, we're going to find the y hat and we're going to find the z. Okay, so let's go into this. So again, the coefficient is going to be just like the coefficient we had before, y dot u divided by u dot u, so inner products. Projection of u onto y, I need to first calculate the coefficient and then multiply that coefficient by the u. All right, so the projection onto y is going to be the coefficient times u, that coefficient being the one I just found. Okay, this one up here. So let's find that coefficient. So y inner product with u, 3, 1, inner product with 1, 1, divided by u inner product with itself. So what we get here is 3.1 is 3 plus 1, so that gives me a 4 over 1 times 1 plus 1 times 1, that gives me a 2. So the coefficient there is 2. So what this means is that if we're looking at the projection of y onto u, what we get is 2 multiplied times the vector 1, 1. So the projection of y onto u is 2, as in the scalar 2, multiplied times the vector 1, 1, which is just equal to the vector 2, 2. Okay? So there you go. That's the projection of u onto y. I misspoke. That's the projection of y onto u. Now, the component that is orthogonal, the component so the component which is orthogonal to this projection will be, again, I've been calling that z. Now, if you think about it, how am I going to find z? I know that 3, 1. Let me go through here. So my vector 3, 1 is equal to y hat, whoops, y hat, which we just found. That's the projection, 2, 2. Plus vector z. So it's pretty clear that z has to be the vector 1, negative 1. Just subtract vector 2, 2 from both sides. So z is going to be the vector 1, negative 1. Got a lot of bold stuff there. I don't need that. Okay, so that's how you find that. So you take, again, I always like to find the coefficient first and then just say, oh, it's the projection onto u is that coefficient multiplied times u. Calculate it. In this case, that gave me 2, 2. So 2, 2 plus what adds to 3, 1? 2, 2 plus 1, negative 1 adds to 3, 1. And if you notice what's happening here, the z and my projection, if you take the inner product of 2, 2 with 1, negative 1, you do get 0. So it'll always be the case that when you project it this way and you find your z, that the z will be orthogonal to the projection, which is a really, really nice property to have. So I want you to go ahead and do the exact same thing for the vectors y equals 3, 1 again, but u now is negative 1, 1. Find the component of y orthogonal to u. And, excuse me, find the projection and then also find the component orthogonal to u. All right, so here's what I did. I took y as 3, 1, u is negative 1, 1. I'm going to project y onto u. So my coefficient is going to be getting y inner product with u divided by u inner product with itself. Interestingly enough, when you take y inner product with u, you get a negative 2. U inner product with u itself gives me a 2. So my coefficient needs to be negative 1. Now, the projection of y onto u is going to be negative 1 times my vector u, which gives me the vector 1, negative 1. So positive 1, negative 1. Now, if you think about 1, negative 1, that's my projection. If I want to add z and create 3, 1, what I would need to do is add 2 to the first entry, and I would need to add 2 to the second entry. So my z is going to be the vector 2, 2. So the component which is orthogonal to the projection will be 2, 2. And again, notice that the projection itself, 1, negative 1, is orthogonal to 2, 2. Now, this was a case where it just kind of came out as happenstance that obviously the component parts are in some ways, just if you go back to the last example, we kind of, in some sense, switched the roles of the projection and the z. Okay, so it kind of came out unique in that way. It doesn't always happen that way by any means. So here's what I'd like you to do. I'd like you to find the orthogonal projection of y onto u for these two vectors. All right, so let's go into calculation of that. Hopefully you did that on your own. If you didn't, obviously push pause and go into calculate it. So what I'm going to do, project y onto u. I'm going to take an inner product of y and u. My y is 6, 7. My u is negative 1, 1. So inner product of y and u divided by inner product of u and u. So 6 times negative 1 is negative 6 plus 7 gives me a 1. So negative 6 plus 7 is 1. In the denominator, I get 1 plus 1, which is 2. So you get 1/2 or 0.5. Okay, I'm going to leave it as 0.5 just because it's a little bit easier to type in. Now, what that means is that the projection is 0.5 times my vector u. So the projection is going to be the vector negative 0.5, positive 0.5. Again, this is just a scalar of my u. And the component, which is orthogonal to the projection, is going to be 6.5 and 6.5. Now, the way I get that is, again, I think of 6, 7 is equal to my projection plus the part that's orthogonal. And when you when you subtract this vector from both sides, what you're going to do is you're going to be adding, or actually, let me just do a subtract. So we subtract that from both sides. What happens? 6 minus a negative 0.5 gives me 6 plus 0.5, which is 6.5. And then 7 minus 0.5 gives me a 6.5. So get 6.5 and 6.5 in for z. Okay? I want you to do one more. We've done a lot of u's, which are negative 1, 1 or 1, 1. Let's do a different u. Let's take 6, 7 and project it onto the vector 2, 1, and then obviously find the component which is orthogonal to u. Push pause and go ahead and do that. Right, so here we go. Let's do the calculations. Again, we're projecting y onto u. So we need to basically, that projection is going to be a coefficient times u. The way I find that coefficient is by using inner products. So I'm going to take 6, 7 inner product with 2, 1. That will give me a 19. So 6 times 2 is 12, plus 7 times 1 is 7. So 12 plus 7 is 19. 2 times 2 is 4. 1 times 1 is 1. 4 plus 1 is 5. So we get a coefficient that is 19/5, which I'm going to write as 3.8. Now again, that's just my coefficient. The projection is going to be 3.8 multiplied times u. So my projection is 3.8 times u. So my projection of y onto u is the vector 7.6, 3.8. So there we go. Now, if you're looking for the component orthogonal to 6, 7, or excuse me, I said that wrong. The component of 6, 7, which is orthogonal to u, what we do is we just take 6, 7 and we subtract the projection that we just found. If you take 6 minus 7.6, you get a negative 1.6. 7 minus 3.8 is 3.2. So the component which is orthogonal to the projection is negative 1.6, 3.2. Now again, think about how this component relates to the projection, or how this component relates to the u itself. Okay, so the u itself was 2, 1. So if we were going to take an inner product with 2, 1, what's going to happen? You're going to get a negative 3.2 plus 3.2, you get a 0. Now, it's obvious that the inner product of, what was this, 7.6, 3.8 is also going to give us 0 because it's just a scalar of my u. All right, so that's the idea there. Okay, that this z I just found is orthogonal to u, and so it's going to be orthogonal to any scalar times u, and my projection is just a scalar times u. Now, let's actually go through this one using this example, and I'll show you kind of what's happening graphically. So graphically, we're trying to project the vector 6, 7 onto 2, 1. Now you'll notice that if I'm breaking things into orthogonal components, I can't draw a line from the end of 6, 7 to the end of 2, 1 and have it be perpendicular. So what we'd have to do is we'd have to sort of extend this line 2, 1 until we can drop basically a perpendicular line down and hit it. So I'm going to do that real quick here. All right, so what I did is I just extended that line out past any place that I needed to. So what's happening is we're breaking this down into component pieces. And what we found is that when you go to 7.63.8, let me actually draw 7.63.8 is somewhere in here. So it's somewhere close to that point. I'm not being very precise, but I'm breaking my vector 6, 7 up into two vectors. This black vector that is running along this purple line, that is, whoops, excuse me, that is my 7.6 3.8 vector. So that's the projection onto that line, 7.63.8. And then this vector here, if I would have started it at the origin, obviously I moved it up here for visual reference, but if I would have started it at the origin, it would have went to the left 1.6 and up 3.2. Okay, so that's the vector negative 1.6, 3.2. That's my vector z. Okay, so here's my projection vector from 0, 0 to there, and then there's my z. Let me see if if I can draw an arrow here. Oh yeah, that's better. I don't know why I didn't do that earlier. So 7, 6, 3, 8, that's one vector, and then the orthogonal vector to it is my z. Okay, so that's what we did. All right. Now, obviously, I did this all in R2. You could have also done the same exact thing in R3. So I'd like you to take and find this orthogonal projection. Find the orthogonal projection of y onto u, and then find the component of y which is orthogonal to u in 3 dimensions in R3. All right, so we're going to project y onto u. It's the same system that we've had before. Projecting y onto u means I just need to scale u in the right way and the coefficient is obviously going to be y dot u divided by u dot u. In this case, I get 7, 3, 5, inner product with 2, 1, 5. That gives me 14 plus 3 plus 25. So 14 plus 3 plus 25 is a 42. Then I get 4 plus 1 plus 25, which is a 30. 42 divided by 30 is a 1.4. Now, again, I'm using these as decimals because it's a little bit easier, and they are, in the last few examples, they ended as rounded to 1 decimal place. Okay, if this were something like 2/3, I would not round a decimal. I'd leave it as the fraction 2/3. But because these decimals have been ending, that's why I've been using those. So all I need to do to find my projection is multiply 1.4 times my vector u. So my vector 1.4, whoops, times u. So take 1.4 times 2 and you get a 2.8. 1.4 times 1 is 1.4. And then 1.4 times 5 is a 7. So the vector that is y projected onto u is 2.8, 1.4, and 7. Now if you want to find the component that is orthogonal to this one, all we have to do is take our original vector y and subtract off the 2.8, 1.4, and 7. And what we'll see there is z is going to have first entry as 4.2, second entry as 1.6, and my last entry is going to be a -2. And if you want to check, you can check that this is going to be orthogonal to the projection. In fact, let's do that. 2.8 times 4.2 plus 1.4 times 1.6, there, minus 2 times 7, you do end up with a 0. Again, just take the inner product of the projection with the z, and you'll see that you get 0. So there you go. We have the projection onto u and the piece which is orthogonal to it. Now, it's harder to draw this because we're in 3 dimensions, but it is the same concept as the thing we had before, as drawing these vectors. All right? I want you to try this on your own. Find the orthogonal projection of y onto u when my u is 3, 0, 3, and my y is 7, 3, 5 once again. Okay, so hopefully you went ahead and did that. If you didn't, push pause because I'm going to go through it. So again, same concept. Y inner product with u, in this case, is going to be 735 inner product with 303 divided by inner product of u times itself. Inner product multiplication there. So 7 times 3 is 21 plus 0 plus 5 times 3 is 15. 21 plus 15 is 36. 3 times 3 is 9. 0, 9, you get 18. 36 over 18 is simply a 2. So that means my projection of y onto u is going to be 606. Just scalar 2 multiplied times 303 as my vector gives me 606. So that's the projection, 606. Now if I want to find the component that's orthogonal, I just take 735 and subtract that 606. That'll give me the z. 7 minus 6 is 1, 3 minus 0 is 3, 5 minus 6 is -1. So the component which is orthogonal is 1, 3, -1. So 1, 3, -1 is going to be the component of 735 which is orthogonal to 606. And you can check each of those claims if you want. Obviously, if you want to, you can, oops, that's from the last problem, confirm that 606 when you add 1, 3, negative 1, in fact gives you 7, 3, 5. And you can also confirm that when you take the inner product of these two, so let's go with the inner product of those two, you get 6 plus 0 minus 6, which is in fact 0. So those two pieces, those two vectors are orthogonal. So what we've done is, again, we've split up this 7, 3, 5 into two vectors which are orthogonal to each other, and one of the vectors is just a scalar times a vector u that I found. So that's the idea of orthogonal projections. Now, orthogonal projections are actually the main topic of section 6.3, and that will also influence 6.4 as well. And so these orthogonal projections are things that we need to be able to do over and over and over again, and you're going to be asked to do over and over and over again. So make sure that you know how to do those. Now, the last part of this section deals with the concept of an orthonormal set. So this goes way back to the beginning. If you remember, the beginning of what we're looking at is orthogonal set. So an orthonormal set is an orthogonal set where every vector is of length 1. So it's an orthogonal set with this additional property that each vector is length 1. Now, why that's nice is because when we're doing projections, notice that my u here was 303 in my last example. It had length square root of 18. If it had length 1, then we'd have been dividing by 1. In fact, if it has length 1, then this denominator just turns to a 1 every time. So in my coefficient, I have to do a lot less calculation if my vectors are of length 1. Or if my u's are of length 1. So it's kind of handy to have orthonormal sets. So let's take this set of two vectors and see if it is orthonormal. All right, so we're looking at the two properties here, orthogonal and normal, meaning each vector has length 1. So let's check those two things out. First off, let's check orthogonality. We only have two vectors in this set, so orthogonal set just means that they're orthogonal to each other. And if I take root 3 over 2 multiplied times negative 1/2, I get negative root 3 over 4. If I take 1/2 times root 3 over 2, I get a positive square root of 3 over 4. Add those together and you get 0. So yes, these two vectors are orthogonal. Therefore, the set is an orthogonal set. Now, in order to see if it's orthonormal, we have to check the length. Now, the length is not the inner product, but actually the square root of the inner product of the vector times itself. So we're going to check the length of this first vector, root 3 over 2, 1/2. When you multiply root 3 times root 3, you get just 3. 2 times 2 gives you 4, so 3/4. 1/2 times 1/2 gives me 1/4, and I get a 1. So again, that's the inner product. The length is the square root of that. So, but again, square root of 1 is 1 as well. So this vector has length 1. If I go to this vector, for very similar reasons, negative 1/2 times itself is a positive 1/4. Root 3 over 2 times root 3 over 2 is going to be 3 over 4. So the inner product is 1. Inner product of the vector times itself is 1. And again, that means that the length of that vector has to be the square root of 1, which is 1. So the length is 1 as well. Hopefully that makes sense. I'm not trying to, maybe if I'd rewrite this, I don't know if this will allow me to rewrite it though. We'll see. So yeah, there we go. Length of this vector, not the perfect thing, but that's okay. There we go. Length of that vector, kind of ugly looking. Length of that vector would be equal to the square root of all that jazz, which is equal to the square root of 1, which is equal to 1. Again, so I just took the inner product. If the inner product is 1, then obviously the square root of that will also be 1. So there we are. So what this is saying is that this set here is orthogonal and each vector has length 1. So this is an orthonormal set. So we have a set which is orthonormal. I want you to take a look at this set, and I want you to see if you can see if it's orthonormal. Push pause on the video and go ahead and do it. Okay, so here's what we did. First off, if you notice these two vectors, 0, 0, -1, actually has a length of 1. You can, again, inner product with itself. 0 squared plus 0 squared. -1 squared is 1. Square root of 1 is 1. Same thing, 0, 0, 1 also has length 1. So our two vectors have length 1. However, when I take the inner product of the two vectors, I end up with a -1. Therefore, these two vectors are not orthogonal. So since the vectors are not orthogonal, the vectors are not orthonormal. All right, so they have the right size, but they do not have orthogonality. I want you to take a look at these vectors and decide if we're dealing with an orthonormal set or not. Push pause on the video and go ahead and figure that out. So what you should notice, or what you should sort of pop out at you, is that actually none of these vectors are of length 1. Just, it suffices, however, to just show that one of them is not length 1. So I'm going to take the 2, 2, -1. If I take the 2, 2, -1 and I find the length, it's going to be the square root of 2 times 2, which is 4, 2 times 2, which is 4, -1 times -1, which is a 1. So it's going to be square root of 4 plus 4 plus 1, which comes out to be a 3 when it's all said and done. So 2, 2, -1 comes out as a 3, or excuse me, it comes out having a length of 3. Okay? So this set is not orthonormal because my vectors are not the correct size. They're not of length 1. By the way, you can check all these other vectors. None of these vectors are of length 1. However, you may have noticed that this is an orthogonal set. If you take 2, 2, -1, and inner product it with 1, 1, 4, you get a 0. If you take 2, 2, -1, inner product it with -1, 1, 0, you end up with a 0. And if you take 1, 1, 4, inner product it with -1, 1, 0, you get a 0. So basically, this is an orthogonal set, but it is not orthonormal. Just like my previous example was a set whose vectors were all length 1, but not orthogonal. So this one is orthogonal, but not orthonormal. So there you go. Now we should know what an orthonormal set is. Obviously, you can create an orthonormal basis. That's a basis, which is an orthonormal set, and so on and so forth. But the orthogonal set and orthogonal basis and the projections are what we're going to use mainly for the next 2 sections. Again, the orthonormal stuff has a really nice property when you're dealing with orthonormal sets in that we can ignore this denominator. If U has length 1, then this denominator basically goes away. So that's the nice thing about orthonormal sets. But again, we're not going to deal with that a whole lot because a lot of times orthonormal sets force us to have ugly fractions or lots of zeros. Excuse me. So that is it for section 6.2, and we will get moving along orthonormal sets. We'll get dealing with more projections in 6.3.